When you flip a light switch, it feels instant, almost like magic. The room brightens in a split second, and we rarely stop to think about what actually happens behind the scenes. But behind that simple click is a remarkable journey, one that spans hundreds of miles, and involves countless people and machines working together. Electricity travels at lightning speed from distant power plants, hydro, wind, or gas, through a vast network of wires, substations, and transformers to reach your home. This network, called the electric grid, is like a superhighway for electrons, connecting rural power sources to city lights and everything in between. The moment you turn something on, a power plant somewhere instantly produces that exact amount of energy for you, matching your demand in real time. Unlike water, electricity can't be stored for later in most cases. It must be generated and delivered the very moment you need it, making timing crucial. Engineers and grid operators constantly balance supply and demand, monitoring the system every second to keep everything running smoothly and prevent blackouts. Let's follow the path of an electron, from the spinning turbine at a power plant, through miles of wires and transformers, all the way to your wall socket. The simple act of turning on a light connects you to a massive, invisible system that powers our world, one that's always working even when you don't see it. The electric grid is the largest machine ever built, an interconnected web of power plants, wires, and substations stretching across North America. It's not just one grid, but several linked together, allowing energy to flow wherever it's needed. Unlike water systems, the grid has almost no storage. Electricity is generated and used in the same instant. Every time you use power, a generator somewhere ramps up to meet your demand. Grid operators act like air traffic controllers, constantly balancing supply and demand to prevent blackouts. Too much or too little power can destabilize the system, so the grid must react instantly to changes. That's why it's built with diverse power plants and complex controls. The grid is a living, dynamic machine, always adjusting to keep your lights on. Most of us never realize the complexity behind every socket. Our electricity use rises and falls throughout the day and year. Mornings and evenings see big spikes as people wake up or return home, while midday and late night are quieter. In summer, heat waves cause massive surges as millions turn on air conditioners. Power companies forecast demand using weather, events, and habits. Even the Super Bowl causes unique spikes. To keep up, they rely on a mix of power sources. Some run constantly, others switch on for peak times. This careful choreography ensures supply always matches our changing needs. It's a 24/7 balancing act, matching energy to our routines. The grid's flexibility is what keeps our lives running smoothly. Power plants play different roles on the grid. Baseload plants, like nuclear and coal, run non-stop, providing a steady foundation of electricity. They're efficient but slow to start, so they stay on all the time. Hydroelectric dams can also provide baseload power, with some flexibility. When demand spikes, fast-reacting peaker plants, usually natural gas, fire up quickly to fill the gap. Peaker plants are less efficient and more expensive, so they're used only when needed. This team approach, steady baseload, plus agile peakers, keeps the grid reliable and responsive. It's how we avoid blackouts during both quiet nights and busy afternoons. Renewables like wind and solar are changing the game. These clean sources of energy are rapidly growing, transforming how we power our world and helping to reduce carbon emissions. Their fuel is free, coming from the sun and wind, but their output is unpredictable and can change from hour to hour, or even minute to minute. We can't control when the sun shines or wind blows, so grid operators must constantly adapt, balancing supply and demand to keep the lights on. To use more renewables, we need ways to store energy for when it's needed most, especially during cloudy days, calm nights, or times of high demand. Giant batteries, like those in California, store excess solar power for use after sunset, helping to smooth out the ups and downs of renewable generation. Pumped storage hydro acts like a water battery, moving water uphill when power is plentiful, then releasing it to generate electricity later, providing a reliable backup. Electric vehicles could one day help too, storing energy at night when demand is low and feeding it back to the grid during peak times, turning millions of cars into a distributed energy resource. Storage is still expensive and not yet widespread, but it's key to building a greener, more resilient grid that can handle more renewables. Solving this challenge is one of today's biggest engineering frontiers, driving innovation in batteries, new materials, and smarter grid technology. The future of energy depends on making storage affordable, efficient, and accessible, unlocking the full potential of renewables for everyone. Once generated, electricity begins an incredible journey, traveling vast distances on high-voltage transmission lines, the superhighways of the grid. These lines stretch for hundreds, sometimes thousands of miles, connecting power plants to cities, towns, and rural communities. High voltage is key to this process. By increasing the voltage, energy loss is minimized, allowing power to move efficiently across great distances. This means electricity can reach even the most remote areas with minimal waste. Alternating current, or AC, is used because it makes it easy to step voltage up for long-distance travel, and then step it down again for safe use in homes and businesses. Transformers play a crucial role in this process. Substations near your town lower the voltage, preparing the electricity for its final journey. From there, power is sent through smaller distribution lines that run along your street and into your neighborhood. The final transformer, mounted on a pole or housed in a green box, steps the voltage down one last time, delivering the safe 120 or 240 volts your home appliances and devices need. This careful, multi-step process is designed to balance efficiency and safety at every stage, ensuring reliable power for everyone. By the time you plug in your phone or turn on a light, electricity has traveled from distant power plants, across towers, substations and transformers, right to your wall outlet. It's a journey powered by science, engineering and teamwork, happening in just milliseconds every moment of every day. Next time you flip a switch, take a moment to appreciate the invisible network working tirelessly for you, bringing light and energy into your life. That's the incredible journey of electricity, powering your world every second and connecting us all in ways we often take for granted.